Solve the following systems of equations by graphing, algebraically using substitution, and algebraically using elimination. I have x minus 3y equals 6 and 2x plus y equals 5. So if I want to graph these, the easiest way sometimes is to get it into slope-intercept form, and then you can plot the intercept and then use the slope to find other points. So I'm going to go ahead and do that for the first equation. So I have x minus 3y equals 6. So I'm going to solve this for y. So I'm going to subtract x from each side. So now I have 3y equals negative x plus 6. Then I'm going to divide each side by negative 3. So now I have y is equal to 1/3 x minus 2. Okay. And I'm going to do the same thing for 2x plus y is equal to 5. So I'm going to subtract the 2x from each side. And that's all I needed to do to solve that one for y. So now I want to plot each one of these. So let's go ahead and plot the first equation. So I have a y-intercept of -2. So I'm going to go ahead and mark that. And then I have a slope of 1/3. So that means I go up 1, right 3. And I can just kind of do that over and over. So up 1, right 3, up 1, right 3. Or I could go down 1, left 3, down 1, left 3, down 1, left 3. So this is kind of overkill, but you can see that uh, they're all following that linear pattern. Okay. When you are solving by graphing, you want to draw your graph as nicely as possible, so everything lines up appropriately. Okay, let's go ahead and plot the other one. So my y-intercept is positive 5. 1, 2, 3, 4, 5. And then my slope is -2. So I'm going to go down 2, right 1, down 2, right 1, down 2, right 1. Well, how about that? I already found where they meet. Okay, so we can see the two lines meet right there. So that's at 3, -1. So by graphing, my solution is x is equal to 3 and y is equal to -1. Okay. Now for the substitution, I already have something started. So for substitution, um, you can solve for one variable and substitute into the other equation. Now, in this case, I've already solved them both for y in order to make it easier for me to graph the two equations. So now these are already solved for y. Now, in general, for substitution, you just need to solve for one of the variables. So if this was just laying around, uh, looking at the first equation, I would have just solved that one for x and then dropped it into the other equation. So substitution. So I'm going to solve the first one for x. So if I solve this for x, I'm going to want to add 3y to both sides. So now I have x is equal to 3y plus 6. Okay, so now I'm going to take this other equation. So I have 2, and where my x is, I'm going to put a set of parentheses because I'm going to replace the x with the 3y plus 6. So this is getting substituted here. Okay, and now I have an equation in one variable that I'm going to solve. So now I have 2 times the quantity of 3y plus 6 plus y is equal to 5. I'm going to distribute the 2. So I get 6y plus 12 plus y is equal to 5. So now I have 7y plus 12 is equal to 5. I'm going to subtract 12 from both sides. And I have 7y is equal to negative 7. And I'm going to divide both sides by 7. So I get y is equal to negative 1. Okay, so there's one of my solutions. Next, so into this equation, I can drop that value of y I just found. So now I have x is equal to 3 times negative 1 plus 6. So what I've done now is I've substituted the solution that I found for y. And now the very last thing here is just an arithmetic problem. So I have x is equal to negative 3 plus 6. So x is equal to 3. Okay, so there's my solution using substitution. Okay, and again, uh, there's many ways that you could complete this using substitution. What my strategy is typically is to look for a variable that I don't have to do any extra work with. So I just had to move that 3y over to the other side, and I already had it solved for x at that point. You could have also solved for this y here in the second equation. That would have been one step to get it by itself as well. And if you want to experiment and try and see what that looks like, feel free to do that and just kind of convince yourself, oh yeah, this works in all kinds of ways. All right. Next, the last way that we're going to do this is elimination. So with elimination, we're using rules that go along with what you're allowed to do to an equation. So the equations as I have them here, I can do the normal algebra things to them. So I can multiply through each side of the equation by a number. Um, and we can also add equations together. And the idea behind that is uh, this x minus 3y is equal to 6. So what I can do if I want to add equations together, if the left-hand side of the first equation is equal to the right-hand side of the first equation, if I wanted to add an x minus 3y to the second equation, I can do that on the left-hand side as long as I add something equivalent to the right-hand side. Okay. Now, what we want to do before we go and start trying to add equations together is we want to manipulate one of them so that something's going to cancel out. So I'm looking, and as they are, if I add the left-hand sides together, nothing's going to cancel out. Now, I'm looking for something easy to do. So if I multiply that first equation through by -2, that's going to give me a -2x, which would cancel out the positive 2x. Or if I multiply the second equation through by +3, that would give me a 3y, which would allow me to do another cancellation. So I'm going to go ahead and just go with the -2. So uh, I'm going to take equation 1 and I'm going to multiply by -2. So I have -2 times x, and then -2 times -3 is going to give me +6y, and then -2 times 6 is going to give me -12. Okay, so now when I add these two equations together, -2x plus 2x gives me 0. 6y plus y gives me 7y. -12 plus 5 gives me -7. Okay, so now I'm at 7y is equal to -7, and I can just solve this for y by dividing both sides by 7. So I have y is equal to -1. And once you have this, you can substitute that -1 into either of the original equations. So if I substitute it into this first equation, I get x minus 3 times -1 is equal to 6. So I have x plus 3 is equal to 6. Subtract the 3 from both sides, and we have x is equal to 3. So now I've gotten x is equal to 3 and y is equal to -1 in 3 different ways. And just to throw a few terms at you, when you have a system of equations and uh, they have one solution like this, you can see uh, graphically what's happening when there is a solution that they're meeting at one point. We would refer to this situation as consistent. So there is a solution, And since we just have this one solution, it's consistent and independent. Okay, time for another example. So solve by graphing, then algebraically using substitution, and then using elimination. So let's go ahead and graph these. So just to move a little bit faster, so graphing, I'm going to skip a few steps. Okay, and then negative 8y is equal to negative 10x minus 4. So I have y is, let's see, so that's going to be positive 5 halves. Oh, no, wait, I'm sorry. So that's going to be positive 5/4 x plus 1/2. Okay, so let's try graphing those. So the first one, we have let's see if we can adjust that a little bit. Okay. All right, that's a bit better. Okay, so doing this one. So -2, and then I'm going to go up 1, 2, 3, 4, 5, and then right 4, 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. And then next. So now I have a y-intercept of 1/2. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, 1. It's getting a little bit high there, so I'll just go down the other way. So 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, and just kind of extending things. Okay, So now graphing this, we can see that the lines are parallel. So when you see parallel lines after graphing them, uh, that means that you have an inconsistent system of equations, which means that there's no solution. Okay, let's look at substitution and see what happens. Do some work I already did, or just for fun, maybe go ahead and just solve for x on one of these instead. So I could have, as I mentioned with the previous one, just used where I solved for y and just set those equal to each other. So let's go ahead and take the 5x minus 4y equals 8. I'm going to add the 4y to both sides. And then I'm going to divide both sides by 5. So now I have 4y plus 8, and then I can just leave that all over 5 if I want. Maybe it might be convenient in a minute. So this is from the first equation. And then I'm going to take the second equation. So now I have 10 times 4y plus 8 over 5. So I'm taking this x and I'm replacing it with what I found from solving the first equation for x. Okay, minus 8y equals negative 4. And conveniently, since I just didn't bother distributing that 5, I can see that, the 10 and the 5, those can cancel out a little bit and just kind of give me a 2 out front. So now I have 2 times the quantity of 4y plus 8 minus 8y is equal to negative 4. So now I have 8y plus 16 minus 8y is equal to negative 4. Well, that's kind of interesting. I have an 8y here and an 8y here. How about that? So note that one's a positive 8y and the other one's a negative, so those are going to cancel out. So now on the left-hand side, all I'm left with is 16. So 16 is equal to negative 4. And I'm going to just kind of let that sink in a little bit. Is that bothering you at all? Well, it should, right? Because this is false. And if that's false, that means no solution. Okay. Next, elimination. The idea is to do something to one equation that's going to cause one of the variables to cancel out when I add them both together. So I'm looking at this and I see I can multiply. So multiply equation 1 by negative 2. So if I do that, I get negative 10x plus 8y is equal to negative 16. And then I'm just going to leave the second equation alone because I'm already set up for success. So I just recopied the second equation. Now I'm going to add the two equations together. So when I do that, negative 10x plus 10x. So by design, I pick negative 2 so that I'd get that negative 10x so that I could eliminate the x variable. So when I add these together, I've done it. But oh no, look what happened. Uh, now I have a positive 8y and a negative 8y. So when I add those together, I get 0. And then negative 16 plus negative 4 gives me negative 20. So I end up with 0 is equal to negative 20. So then that means no solution because it's false. So that false statement that you end up with indicates that there's no solution because we have an inconsistent system of equations. All right, the last example. So solve by graphing, and then algebraically using substitution, and then using elimination. So I'm looking at this one. So that one, I can easily find y is equal to 7x minus 3. This one over here, so I see, right, negative 2y is equal to negative 14x plus 6, and then I can divide everything through by negative 2. So I get y is equal to 7x minus 3. Hey, these are the same. How about that? Well, let's go ahead and graph them. Well, I'll just graph one of them, but that means I'm graphing both. Okay, so let's fix my axes here a little bit. Okay, so negative 3 and then up 7. So there's 3, 4, 5, 6, 7, and then right 1. So 2, 3, 4, 5, 6, 7. Okay, so if I graph the other one, they would just overlap. So these are the same, right? So in this situation, the, graphs overlap is how you can think of it, which means that if you think back to that first example where we had one solution, it was consistent, uh, and that's all nice and easy. That's the one that we like to deal with because we don't have to think about more complicated stuff. We get one answer. It's nice. The second one we looked at, we ended up with two parallel lines. They didn't touch anywhere, right? So these parallel lines in two-dimensional space, uh, flat space, never cross each other, which means that there's never going to be a solution. And well, what if we had two parallel lines except they were the same line, right? So they have the same slope, they have the same y-intercept. Uh, so this is the situation where we have infinitely many solutions. Okay. And of course, you could, just state that the infinite number of solutions is just from this equation. So every ordered pair that equation cranks out is a solution to that original system of equations. Okay. And then here we call this consistent dependent. Okay. All right. So there's the graphical method. So if when you graph the system of equations, the graphs overlap each other, or in other words, they're the same graph, then that means you have infinite solutions. And those infinite solutions are characterized by the one equation that they both happen to be. Okay, so let's see what this looks like if we're using substitution. First equation, I can solve for y in one step. So I have y is equal to 7x minus 3. And then into the second equation it goes. So in this case, I'm going to replace the y with 7x minus 3. Okay. So let's distribute that -2. So I have negative 14x plus 6 is equal to 6. So we can see these 14x's cancel each other out. And then I finally end up with 6 is equal to 6, which is true, which means I have infinite solutions. And of course, uh, the solutions are all of the ordered pairs xy that oops, satisfy. And however you want to state that, you could, say y equals 7x minus 3, or you could say 7x plus y equals -3. Any version of that equation, uh, you can say. Okay, so that's substitution. Let's do this with elimination. Well, I've been, kind of hitting that first equation. Let's hit the second equation with something. So maybe I noticed that, oh, that 14x, if I multiply that by a half, then I can cancel out the -7. So multiply equation 2 by +1/2. So the first equation is going to come down as is. And then the second equation That's going to be, so 14 times a half is going to be 7. And then -2 times a half is going to be 1 or -1. So that's just going to give me minus y. 6 times a half is 3. Okay, so now I'm going to add these together. So -7x plus 7x is 0. Y minus y, or y plus -y, is 0. And then -3 plus 3 is 0. So now I have 0 plus 0 is equal to 0. So 0 is equal to 0 is a true statement. So, and again, we get that infinitely many solutions. And I'm not going to restate the thing I said earlier where you could say, uh, or at least not write it down, but the solutions are all of the ordered pairs that satisfy any version of the equation